That is my cue. All right. Good morning, everyone. Thanks for joining our fourth webinar for the Industrial Innovation Initiative Learning Series. And so this webinar will be focusing on biofuels and the pulp and paper sector. And so we decided to kind of join these two sectors. I mean, we think that there's a lot of ways that they kind of relate to one another and really have a lot of different relationships with one another. So this could kind of be a combined webinar. So we will get started today. Kate, could you go to the next slide, please? So just a quick intro with the agenda. I'll provide a couple updates for I3 on just some upcoming dates for everyone. And then we will dive into some great speakers. We have 4 speakers today that will go through the overview of both the sectors, as well as diving into some decarbonization initiatives and projects for both of the sectors. Next slide, please. So a couple important dates coming up. So as we have mentioned before, WRI and GPI have been working on a level setting white paper, and we are looking to share that with all of you the week of January 4th. And that'll provide some time before the plenary group meeting on the 14th for everyone to review and be ready for the discussions that we'll have on that day. On the 6th of January, it will be our last sector learning series webinar. We have made it to the end, and it'll be the refining sector. And then on the 14th, as I mentioned, we will be having our launch of the plenary group meeting. So it'll be a large group meeting that we can really dive into strategy and what we'd like to see for I3 in 2021. So we can get started with our presentations today. So we'll be having 4 presentations from some great speakers. So Brendan Jordan, the Vice President of the Transportation Fuels team at GPI, will be providing us with an overview of both the biofuels and the pulp and paper sectors. Brendan joined GPI in 2004 and has 10 years of experience in leading initiatives to promote deployment of clean energy technology. He serves as lead staff of the Bioeconomy Coalition of Minnesota and has served for 6 years in a lead facilitation role for advisory groups to the Midwestern Governors Association, focusing on fuels and transportation. Followed by Brendan, we'll hear from Daniel Sanchez, who will give us an overview of projects in the pulp and paper sector. So Daniel's assistant specialist at the University of California, Berkeley, and is studying the commercialization and deployment of energy technologies that remove carbon dioxide from the atmosphere, and he currently runs the Carbon Removal Lab. Daniel's work and engagement spans academic, non-governmental, and governmental sectors. Prior to joining UC Berkeley, Daniel was a fellow serving the office of Senator Michael Bennet and has previously held positions with ARPA-E, Green for All, and the California Public Utilities Commission. Following that presentation, we will be hearing from Paul Koehler, the Vice President of Corporate Development at Pacific Ethanol, who will then provide their decarbonization initiatives and perspectives. Paul has over 28 years of business experience in ethanol and renewable electricity industries. At Pacific Ethanol, Paul has led the grain and co-product division since 2011 and corporate development since joining the company in 2005. Previously, Paul has served as a Director of Business Development for PPM Energy, leading PPM's effort to develop and acquire several wind power projects. Paul was also a co-founder of Re-Energy and has worked for Portland General Electric and Enron in electricity trading, marketing, and commodity risk management. And finally, we will be hearing from John Holladay, who will then provide his insights on low-carbon biofuel strategies. John is the Energy and Environment Directorate at Pacific Northwest National Laboratory. He is responsible for PNNL's $15 million per year research portfolio on biofuels, products, and energy, including sustainable utilization of terrestrial biomass and marine systems to fuels and chemicals via chemical and biological catalysis. John has had past experience in organizing consortia of national laboratories, industry, and academia, including the National Advanced Biofuels Consortium and the National Alliance for Advanced Biofuels and Bioproducts. So again, 4 great speakers today, and so we will get this started with Brendan Jordan at the Great Plains Institute. So Brendan, take it away.
Great, thank you very much, and I'm glad to have the opportunity to speak to the group. I'm going to keep my remarks fairly high level. We have some great experts here today who can dig into some of the specific strategies and what the opportunities look like. If you wouldn't mind going to my next slide. and actually just the next one as well. So, I want to just start by talking about why this is important. And so we're focused today on two sections of the industrial sector, ethanol and pulp and paper. By themselves, these, they represent a significant part of overall industrial emissions. Talking with Dan the other day, it's about 200 million tons per year combined between those sectors, which, my simple back of the envelope math suggests it's, close to about 13% of total industrial CO2 emissions. So it's a large enough segment that we need to take it seriously. It's important in its own right. But I actually think it has some importance beyond just the role of these sectors in broader industrial emissions. And I think it's actually crucial to thinking more broadly about economy-wide decarbonization. First of all, this is a driver for CCS, right? These are particularly ethanol has been identified as one of the low-cost sources of CO2. And so, as we're looking to deploy CCS technology, that industry needs to be at the table, and I think intends to be at the table in figuring out how to build out a multi-state CCS infrastructure. It connects to other policy initiatives like the growing interest in a clean fuel policy, which can be alongside policies like the 45Q tax credit, can help drive additional carbon capture and storage. So I think there's a suite of technologies. CCS is the big one that are ready or in development. Pulp and paper is a higher cost deployment scenario for CCS, but I think also a near-term opportunity. But I think kind of going beyond that, I think there's potential with these two industries to have impact beyond just industrial sector emissions because of the resource base that they draw on. And, the biofuels industry is obviously a crucial part of agriculture. And so there's opportunities beyond what we would strictly call industrial sector emissions to pull in, broader emissions reductions from agriculture. And obviously in pulp and paper's, interconnected with forestry, and many mitigation scenarios, draw a lot on, so-called natural solutions, which, as I'll note, hinges, I think, a lot on having management take place within forests, which requires which requires an industry that's able to do that management and the ability to have loggers in the forest. So I think, these sectors are really crucial for deploying CCS. I think they're crucial early opportunities to demonstrate BECCS, which is bioenergy plus carbon capture and storage, which creates this opportunity for, carbon negative energy. And BECCS is, this huge and somewhat daunting part of the global mitigation scenarios, and people sometimes view this with skepticism, right? Can we really deploy that much BECCS? But what I think is really key is not, maybe we don't need to worry so much about exactly how large the opportunity is, but can we start with some of the opportunities that we know make sense, and and go from there. And I think these are, kind of the two of the earliest nearest term BECCS opportunities. Final point here is that these industries are politically essential, and almost by definition, these are industries that operate in red states or in red parts of states. I've collaborated a lot with both of these industries over the year. I'll kind of tell a little bit of an example from Minnesota, where we do some work on state policy. And I think what I've learned working on bio-based technologies, advanced biofuel technologies, doing a lot of work with the forest products industry, is just understanding that you've got the industry, but you've also got a whole network of industry stakeholders, county governments, economic development groups, utilities, state legislators, federal legislators. And I think the really important thing to note is that, you know, in these areas where you have perhaps only, it's, you know, it's a rural area, you perhaps have only a few primary industries that represent a big part of the total economy. You know, you've got this whole network of people that are looking to say yes to investments and projects. And sometimes I think the tendency of the environmental community is to focus on what they want to say no to. But I think it's just really critical that if, you know, if we find the opportunities that offer a climate benefit and also create an opportunity for jobs and economic impact, um, we can say yes to things and have a large network of supporters that want to help make those things a reality and try to align economic and environmental benefit. And so if you wouldn't mind moving to the next slide, please. So, you know, I think it's a climate imperative to find that alignment and find projects to say yes to. I think CCS at ethanol and pulp and paper should be one of those early opportunities where we have a way to say yes to some new investment that would lead to jobs and economic opportunity and also carbon removal. I think we can kind of move beyond that as well and look at, you know, CCS at other kind of bio-based technologies, perhaps renewable natural gas projects. You know, effectively you're just doing natural gas processing, and should be, you know, should represent an opportunity for CCS. Maybe there's emerging new kind of dedicated BECCS projects that come a little bit later, you know, municipal solid waste, you know, dedicated, you know, advanced biofuel projects with CCS. Um, a lot of analysis has been done on these types of projects, and maybe it's time to start looking at how we actually deploy things. I also think too, you know, just note that there are carbon removal opportunities using bio-based feedstocks that are not strictly limited to CCS. I think CCS offers the most carbon benefit, but you know, there's all this innovation going on in engineered wood products that can, for example, substitute for concrete and steel in buildings, and, you know, by the way, store carbon over an extended period of time in that building. Opportunities like biochar that can be potentially a soil amendment and can represent long-term storage of carbon from bio-based feedstocks. Bioplastics potentially are a similar opportunity, and they may be part of an overall portfolio approach. They may be done in places where you maybe are not as close to the CCS resource and may be favored. You know, thinking about the connections, again, agricultural soils, not part of industry, right? Not strictly speaking industrial emissions, but industry is going to be crucial in connecting with that sector. And so, and I think, you know, biofuels in particular, you've got an opportunity as you're looking at the life cycle assessment of biofuel production. You know, a big part of that is agricultural emissions on the farm, soil organic carbon storage, nitrous oxide emissions reductions from soil carbon management, and the ethanol industry, by accessing policies, clean fuel policies, voluntary market, you know, corporate procurement policies, 45Q, can help, you know, pull in broader emissions reductions, not just CCS, but also, you know, upstream emissions related to feedstock production, and potentially really help contribute to agricultural. And on the forestry side, of course, you know, pulp and paper's, you know, a critical stakeholder there, sourcing feedstock from forests. And one of the things I would say is that, you know, we know that there's a lot of talk about natural carbon solutions. I think if you wouldn't mind going to the next slide. You know, we hear a lot about natural solutions managing forests to store carbon. I think a lot of those things require management and disturbance. We hear about, you know, the critical need to remove bug kill wood, for example, and replant different species. There's the whole issue of adaptation, where you might need to shift the species composition of forests over time. And there's other management strategies that, you know, focus on different trees and different rotations that store more carbon in standing wood litter, wood litter in soils and forests. So many of those strategies require management, and management requires loggers. And to employ loggers, you need a market for wood. And we can be thoughtful about what wood we're talking about, whether that's residuals or bug kill, or really targeting the things that need to be removed to have that climate benefit in the forest. But you need industry, and we really need more of an integrated approach, I think, to looking at what industrial opportunities offer the most carbon benefit, and how do they integrate the best with the management strategies that offer the most carbon benefit from a forest management perspective. So overall, I think we really need to devote a lot more time, I think, to thinking about this in a comprehensive way. I'm really excited about the speakers we have today, digging into some of these opportunities specific to pulp and paper and ethanol, and I think I'll leave it at that for now.
Great, thanks, Brendan. Thanks for that introduction. So we now are going to dive deeper into that potential for the BECCS projects in the pulp and paper sector with Dan Sanchez. So Dan, please take it away.
Hi, everyone. Good morning. It's a pleasure to be speaking with you. As Brendan mentioned, I'm going to be picking up on some of the broad themes, and it's always a pleasure to follow speaking him. I think he does such a great job of kind of framing the relevant question here. When we're talking about biomass and bioproducts, we're talking about industries that do have the opportunity to remove carbon dioxide from the atmosphere and place it into either long-lived storage or in long-lived products. And I think it's something that climate advocates need to be deeply engaged in, as there are huge industries, multi-million-dollar investments, and real physical carbon flowing around in these systems that needs to be contended with. So I want to speak today about the opportunity for carbon capture and storage in the U.S. pulp and paper industry. And this is part of an analysis I did with a team of colleagues at North Carolina State University. That was led by an assistant professor there named Joe Sagas. He runs something called the Biocarbon Product and Removal and Utilization Lab. And he is a really outstanding engineer and systems analyst, and did a lot of the underlying work for the results I'm about to show you today. I should also note this work was sponsored originally by the Climate Works Foundation. Let's go ahead to the next slide. So what I'm showing here are the approximately 205 what's called an integrated kraft pulp and paper mill in the United States. Integrated kraft pulp and paper, these all signify specific things to people in the pulp and paper industry and in the forestry industry. What we're talking about here are large integrated mills that not only produce pulp, which is the first thing you make from wood, but also turns that pulp into paper. They typically are the ones that are largest. They have the highest throughput. They have the most stable investment, and they also have the largest sources of CO2 emissions because they're taking the wood all of the way from wood to its final, usually finished paper product. So there are about 205 of these mills operating, at scale across the United States right now, and they span a broad geography, mostly in the east where forests are most productive, but including a broad swath of the Pacific Northwest as well. And as you can see, broad dispersion, including across rural areas, red states, places we need to engage critically to accelerate climate and carbon solutions. I just also have underneath just a kind of an initial indication of where we think there are suitable geologic formations that store CO2 from these pulp and paper mills, and about 45% of those mills and their associated emissions are on top of what we consider to be suitable geologic storage in the United States. Many of those in the Midwest and the Southeast. Again, providing some interesting political opportunities. Next slide. And just across those 205 integrated kraft mills, it's important to note that EPA's classification of the CO2 emissions, that is mandatory and required under the greenhouse gas reporting rule, largely misses most of these emissions. And that is because 77% of the emissions from the US pulp and paper industry is biogenic in origin or derived from biomass. And there are more relaxed rules around reporting biogenic emissions under current EPA greenhouse gas reporting. So instead of working with EPA data to really understand this, my colleagues and I work with a proprietary industry database to really understand kind of the current state of the industry, as well as the wood utilization, the sizes of their units, their production, and their relevant overall CO2 emissions. Again, most importantly, 77% of the emissions from pulp and paper mills is biogenic in origin. Now that varies between these mills that are optimizing their costs and their profits. But much of that is derived from, say, black liquor, a byproduct where energy is recovered from the pulping process. Waste wood is also burned in supplemental boilers all across pulp and paper mills, and really adding those two things together gets you really the biogenic sources of CO2 in these mills. We also have natural gas, a little bit of coal, and residual small fuels like petcoke and fuel oil that is going into some of these refineries. Some of these mills. Next slide. And what we're looking at here is what we consider to be kind of the most mature form of carbon capture and sequestration. I don't want to bore everyone with the details, but we're talking about using liquid solvents, amine solutions to capture CO2. Monoethanolamine, or MEA, is a well-known and well-tested solvent. These are the systems that are in deployment at coal-fired units across the world today. These systems, though, have significant capital costs, particularly to build the columns, build the CO2 separation system, but also significant energy costs that are related to the regeneration of the solvent. So after the monoethanolamine binds to the CO2, you need to regenerate to separate the CO2 back off, and that requires a significant energy penalty. Which those two things, those capital costs and those energy costs, really drive the cost of carbon capture and sequestration that we see in this industry. Next slide. And this is a complicated slide, and I don't want to go too deep into the engineering today. If you could press enter once, there are three sources of CO2 that really come from an integrated kraft mill. Two of those are boilers. One is a recovery boiler that combusts black liquor to regenerate the sorbent and complete the pulp process. But there are also other multi-fuel boilers that provide heat across a pulp and paper mill. And then, of course, the chemical regeneration of self in a lime kiln is another source of CO2 emissions. And all of these contain a mixture of biogenic and fossil sources. And all of these are targets for potential post-combustion CO2 capture at these mills. Next slide. And again, as I mentioned before, there's a broad breakdown of the CO2 emissions that we estimate from these different boilers, these lime kilns, and these recovery boilers. Multi-fuel boilers live up to their name. They burn a lot of different things, including both waste wood and natural gas and coal in their largest supplies. Lime kilns, importantly, are largely fossil, where recovery boilers are largely biogenic in their origin. And if you could just press enter once, I want to call out two things that I think are really interesting here. Lime kilns actually have a much higher CO2 concentration, which means that they, in theory, should have a lower cost of CO2 capture. The problem is that lime kilns are a relatively small portion of emissions within pulp and paper facilities. They only comprise about 9% of overall emissions. So you really have to balance, the idea that you can go after this more concentrated source of CO2 for capture and sequestration, but then also the fact that these are smaller units, so you don't benefit from the economies of scale of building larger CO2 capture units. Next slide. And so we, again, working with an industry database, looking industry-wide, try to understand the operations at these existing 205 facilities, the fuels they combust, and to estimate their cost of CO2 capture using correlations based on flow rate and CO2 concentration. Next slide. And of course, the motivation for this was to understand whether or not these opportunities could be profitable under the existing Section 45Q tax credit. I'm sure this is nothing that this group needs to hear about, but other industrial facilities that capture over 100,000 tons of CO2 per year and store them in permanent geologic sequestration are eligible for a tax credit of up to $50 per ton for a 12-year period. And that we really wanted to evaluate the economics of these facilities under that framework. Next slide. So we again, for these 205 sites and the different unit operations that release CO2 there, we estimated these costs. There's a lot of data here. It's going to be hard to walk through it very quickly. I should note that these costs are conservative. In that we assume you have to build a new boiler. We assume that you're using biomass to fire that boiler. We're making some relatively conservative assumptions here, but we find that with a $50 per ton of CO2 subsidy, 45Q acts similarly to that, that we are just on the kind of the precipice of affordability. Similarly to coal-fired power plants, where 45Q is close, but not all it's going to take in order to make carbon capture and sequestration financially profitable at these facilities right now. So what we did is we started to look at more specific opportunities that might arise at specific mills due to mill-specific conditions. And we actually found that there was, when you're considering, say, opportunities to utilize waste heat or to utilize idled capacity, including boilers that are at these, that are decommissioned or idled or mothballed at these facilities, that was really where we were finding the very low cost and profitable near-term opportunities in the industry. Next slide. So just to show some of the conclusions, we did find significant economic returns at pulp and paper mills, particularly those with waste heat resources, idle boilers, and stranding assets, and proximity to suitable geologic storage sites. I mentioned about 40% of the CO2, or 40% of the emissions from these facilities is co-located with suitable geologic storage. So, an exciting prospect, but not necessarily the big, super easy economic win that we have right now, which I think we actually might have in fuels production and in the ethanol sector. And I look forward to hearing Paul's upcoming comments around those opportunities. That being said, I think there are niche opportunities, there are near-term opportunities with, again, for folks in the industry who truly understand where there's opportunities for waste heat and power generation at these mills, or where there are idling and stranded assets. I think that's an opportunity for much more diligence to understand the capture opportunities. I should also note that there are a lot of other alternative techniques for CO2 capture at pulp and paper mills. You're already running a lime kiln, a carbonation process, and opportunities to fire that, or partially co-fire or fully co-fire those lime kilns with oxyfuel present some interesting CO2 capture opportunities, as well as other opportunities to think about calcium looping integration in pulp and paper mills. That is deep in engineering weeds, but I wanted to flag that for anyone who is interested. And next slide. If anyone's interested in really getting all of the details here and learning more about the analysis that we did, taking a deeper look at the industry and the opportunities, I'd point all of them to this paper that came out earlier this year, again with my colleague Joe Sagas as a first author, and that was published in Energy and Environmental Science, which is a really great engineering and climate journal. So I'll stop here. I'm sure we'll have a lot more time for discussion. Thank you.
Thanks, Dan. Thanks for that deep dive into the CCS world of pulp and paper, and shows a lot of complexities and opportunities alike. So thank you so much. Next, we'll hear from Paul on the Pacific Ethanol's decarbonization initiatives and perspectives. So Paul, take it away.
There we go. Okay, hello, and thank you for inviting me to speak about how the ethanol industry is decarbonizing transportation fuels through practical and innovative measures. Um, as, as introduced, I'm Paul Koehler. I'm Vice President of Corporate Development for Pacific Ethanol, and we produce specialty alcohols, protein feeds, and renewable fuel at 7 facilities located in the states of Illinois, Idaho, Oregon, and California. As many of you probably know, the U.S. ethanol industry has struggled over the last several years, driven by oversupply, inconsistent public policy, volatile commodity markets, and what really have turned out to be anemic crush margins. And COVID has struck an additional blow to our industry as well, as fuel demand was down initially by as much as 50% last spring, and now is down 15% compared to the same time last year. Too many Zoom meetings or something like that, people staying at home, not so much transportation fuel. To stay afloat as an industry and as a company, we are all investing in better co-product utilization of our plants. And just as it was like 10 years ago, when distillers corn oil was the new value-added product, which added meaningful bottom line earnings, now the industry is further diversifying its product mix, increasing its revenues, and relying less on ethanol sales for profitable operations. These products include high quality alcohol used in hand sanitizer as an example, high protein feed. Protein markets continue to be very strong worldwide, and carbon monetized through carbon credits, low carbon fuel standard, renewable fuel standard, and 45Q tax credits. Remember, when processing corn, 1/3 goes to ethanol, 1/3 goes to feed, and 1/3 goes to biogenic CO2. CO2 is the most abundant and underutilized co-product of ethanol production. The low carbon fuel standard is a big demand driver for investments to decarbonize ethanol production, and has catalyzed many low carbon projects industry-wide. Let me just briefly discuss the LCFS before diving into some projects. The LCFS is designed to decrease the carbon intensity of California's transportation fuel pool and provide an increasing range of low carbon and renewable alternatives, which reduce petroleum dependency and achieve air quality benefits. The LCFS is a key part of California's stated goal to reduce greenhouse gas emissions to 40% below the 1990 levels by 2030. LCFS markets allow producers to monetize the carbon value through the sale of transportation fuel, be it from ethanol, CNG, electricity, hydrogen, or any prime mover energy used for transportation. It should be noted also that while the ethanol industry has lived through volatile and disruptive markets, the carbon market in California has been stable. The pricing for an LCFS credit is consistently around $200 per ton. And supporting this demand is a steep compliance curve required by state law in order to achieve the emission reduction goals over the next 20 years. I also should note the LCFS market is distinct from the cap and trade credit market, which regulates emissions from industry. Cap and trade program in California has successfully supported low carbon investments in industries and in agriculture. As an example, there are many dairy digesters developed in California that are partially funded by the state's AB 32 funds. Cap and trade credits currently sell around $17 per ton, distinct and separate from the LCFS market. So before a discussion of projects, a quick note on how impactful the LCFS is. The $200 per ton value equates to about 1.6 cents per gallon per CI point. So even the smallest projects have a meaningful impact. For example, at a 60 million gallon a year plant, if you were to move CI by just 1 point, that is nearly $1 million in annual value. For a quick review of projects, let me do a quick review of some key projects implemented at some ethanol plants here. First, and not surprisingly, are just processing efficiencies for reducing operating costs and improved CI scores. This includes things like variable speed drives, replacing constant motor drives to moderate as production moderates. It focuses on steam efficiencies, making sure you're not leaking steam through your system, and also making sure that the steam is being most efficiently utilized in all the heat exchanging that occurs in a process. And then burner efficiencies and boiler optimizations. We use a lot of steam in the ethanol processing, and having efficient burners makes a big difference. This can adjust your CI score, CI of course meaning carbon intensity, CI score by 1 to 3 points. And so in addition to creating just operational efficiencies and cost savings, you're bringing over $1 million or more to the bottom line in carbon value to these projects. At our Madera, California project, we installed a membrane separation system to separate the water from alcohol in the finishing stages of distillation. This reduces the energy demand in that final dehydration step and improves the CI score by about 1.5 points. Incidentally, it also smoothed out operation. So from a plant operator's standpoint, it was much more steady operation, steady production, which adds its own level of efficiency and yield for the plant. We installed the White Fox system. They've got a good system, and that system has been deployed at several locations industry-wide. Another way that plants have decarbonized is through producing cellulosic ethanol with corn fiber. That is part of the corn kernel. It's distinct from the corn starch for conversion to sugars, then fermented to alcohol. There are several applications for this, and some have been more successful than others. These streams do gain the value of the D3 RIN under the RFS, which is nearly $2 per gallon, and the process has an LCFS score that is about half of that produced from cornstarch. I should note that while the D3 RIN market has suffered during the Trump administration because of EPA's resistance to accept and certify such pathways, the California has embraced corn fiber ethanol in the LCFS market. The California Air Resources Board has issued Pacific Ethanol and several other producers CI scores for cellulosic ethanol from corn fiber in and around 35 points. An additional project that provides significant carbon value is mechanical vapor recompression. This is an interesting one in that it combines achieving thermal efficiencies with low carbon energy sources. Ethanol plants are steam hogs. We love steam. Traditionally fired by natural gas and demanding 18,000 to 25,000 BTUs per gallon, or even more for less efficient plants. Steam is used throughout the process with many heat exchangers and cooling and reheating, and all that is required to convert corn to ethanol. And when spent, the steam returns as condensate to then be reboiled into steam again. The MVR captures the steam before its energy is spent, and it is compressed for further use. This reduces natural gas demand by about 50%, with a corresponding reduction of CI of 12 to 15 points. However, electrical demand will increase to run the compressors needed to pressure up the recovered vapor. It should be noted the carbon intensity of grid power is less than natural gas. particularly in California, where the grid is comprised of lots of renewables. I love knowing that 15% of the California grid is coming from solar sources. And being a veteran in the utility business back in the day, it was well less than 1%. The net impact reducing natural gas and increasing electricity with this MVR technology can reduce the carbon score by 7 points or more, which is about 12 cents per gallon, and meaningful impact on production economics of ethanol plants and with an attractive payback. Renewable natural gas used directly in ethanol production or converted to CNG or to electricity for transportation has increasingly been sold into the California market. The Calgren Biofuels 60 million gallon a year ethanol plant in Pixley, California is a great example of leveraging its geographical position, proximate to many dairies, and as a producer of low carbon fuels in California. They have developed an integrated system of over a dozen dairy digesters which capture the methane gas from cow manure and transport it by pipeline to its ethanol plant. Burning biogas from dairy digesters for production of steam at an ethanol plant has a significant impact on CI score. Many dairy digester projects have CI scores of greater than minus 200 points. This is a negative CI, which takes into the consideration in the analysis the methane avoidance from current practice of open air lagoons for dairy manure. Methane has a 15 to 20 times greater impact on climate change than CO2. So capturing the methane and burning it is a big climate benefit. These projects also are very expensive on a $1 per BTU basis, at least 10 to 15 times more expensive than buying natural gas from the pipeline. So the low carbon fuel standard benefit is required to make such projects economic. There are many other such projects at plants throughout the industry, some from dairy digesters, others from landfill gas, others from biogas self-generated from streams coming out of the ethanol process. Finally, carbon capture is among the best ways to decarbonize ethanol. As mentioned earlier, 1/3 of the corn kernel is CO2, and ethanol plants produce clean CO2 with purities of 98% or better, which is then further cleaned, processed, and sold typically for beverage and food processing as liquid CO2 or dry ice, pretty much in high demand right now with the vaccines being distributed. But only about 45 of the 200 ethanol plants process CO2 for commercial sale. The rest is simply vented to atmosphere. The fossil fuel industry has long injected CO2 into existing oil wells to enhance oil recovery, as we all know. But now with the 45Q tax credit, the LCFS, and cap and trade incentives, there are a host of projects at ethanol facilities being developed for direct injection into saline geologic storage. ADM was the first mover with this, with its Decatur, Illinois project, which now injects up to 1 million tons per year into the St. Simon geologic formation at approximately 8,000 feet deep. This project took many, many years to develop and get permitted, and it has paved the way for follow-on projects, some of which include connecting ethanol plants in the Midwest by pipeline to deliver to storage in Texas or Oklahoma, some aggregating sources proximate to a nearby sink, and some individually developing independent storage capacity. Pacific Ethanol's Pekin, Illinois site is directly over the St. Simon formation, the same one that ADM has used, a little shallower at about 7,000 feet. And it has good characteristics for developing a storage facility. Our plants produce 750,000 tons per year of CO2 at the Pekin, Illinois site. That's an enviable scale for carbon capture at an ethanol plant. This is an exciting project because of our geography, right over good geology, and with an ability to capture not only the 45Q tax credit, but also the revenue value from the sale of fuel-grade ethanol into the LCFS markets. Capturing CO2 and storing it will produce a CI benefit of between 25 to 30 points. This creates a revenue stream of approximately 50 cents a gallon. Or another way to look at it is to add the $200 per ton for LCFS and the $50 per ton from 45Q for a total of $250 per ton of revenue. These project economics are very compelling. What's the future of the LCFS? Well, this program is secure in California. It is secure in Oregon under a clean fuel program, very similar to California, trades more at $125 range. It's under legislation in Washington. Canada is looking at a national fuel standard. Midwest states, New England also are moving forward with statewide legislations on fuel standards. And federally, as the renewable fuel standard is reconsidered beyond 2022, there is talk of a national fuel standard as well. So, as I was saying earlier, the LCFS market has been stable and secure market for carbon, which has attracted important investment that produces good returns, diversifies our industry's product mix, and decarbonizes the production of transportation fuel. So that, I will wait for comments and questions, and I'm looking forward to further discussion. Thank you.
Thanks, Paul, and thanks for really going through all of those many options that your industry does have for decarbonization. Next, we'll hear from John Holladay and on additional biofuel strategies for decarbonization. So John, please take it away.
All right, well, thank you very much. Can we go to the first slide? Next slide. There we go. So I really appreciate being able to listen to Paul and Daniel. I learned an awful lot. Thank you so much. I'm going to begin by talking about biofuels today, and then just quickly going through. I think as people know, in the U.S., biofuel production is, or biofuel use is just above 18 billion gallons, and 97% of that is coming from how plants store energy, right? So this is from starch and from vegetable oils. And the Department of Energy and others have invested billions of dollars over the last 10 years over moving into cellulosic and biofuels, and it just hasn't taken off. The amount of cellulosic biofuels that are produced in the US today, other than renewable methane, is less than 0.04%. So it's quite small. It was about, in the US, about 5 million gallons, and total use in the US is about 10 million gallons. And so as Paul talked about finding this additional use of getting a D3 RIN from the corn fiber, that is a compelling thing. But let's move on. So emerging with the lack of real movement in cellulosic biofuels has been consideration of other waste carbon sources. So these are vast and varied. They can be municipal solid waste, plastics and resins. I'm going to focus most of my talk on wet sludges and manures. I will note that today about 3% of our biofuels do come from waste carbon. This would include fats and greases that go into renewable diesel, as well as the renewable natural gas, which is for the most part coming from landfills, with addition of some anaerobic digestion, as was also discussed earlier. So let's move on. So I think last week, at the last talk, you heard from Laurel Harmon, who talked about one source of waste carbon is industrial waste gas. And I think this is really important. for us to start taking a look and being able to do things with these industrial waste gases. With the LanzaTech example, of course, they're looking at a still mill gas, which is rich in carbon monoxide, and can take that to ethanol. And right now, in their plant that's located in China, more than 13 million gallons have been produced to date, 70,000 tons of CO2 avoided. Also, opportunities in looking at refinery gases that are rich in carbon monoxide, hydrogen, and carbon dioxide. And this also can be taken to ethanol. Now, in the US, this is not available for our RINs, but it is available for the California Low Carbon Fuel Standard. CO2, a lot of work in Europe is looking at CO2 making fuels. I have a lot of material on that. I'm not going to cover that today, but if there's questions, I'd be happy to talk about that. The amount of electricity that's required is phenomenal, and so high that the overall CO2 savings can be not as great as people might think, based on even a clean grid. So anyway, let's go ahead and move on. You know, Paul talked about the challenges that the ethanols have, that we're largely a saturated market right now. And so one of those things that we are looking at is being able to take ethanol and use that as a platform to make other high quality fuels, chemicals, lubes, and so forth. I don't want to spend a whole lot of time on this, but just wanted to mention that. For sustainable aviation fuel is one of those areas that there's been quite a bit of excitement around, of being able to find high quality fuels that we can use for vehicles that are really challenging to electrify. And so I think that is an important source of what we can do with ethanol. Next slide, please. But let's consider a little bit deeper the use of some sludges and some of the opportunities that these can present. Not practiced today, but it's right now at a pilot scale being looked at both in the United States and Europe and Australia. So these sludges come from wastewater, from municipal wastewater. They can come from manures. We look at algae blooms, food waste. There's a number of different sources. And they can be used alone or as mixtures with each other or mixtures with wood and stover. Pictured here, you can see sludge from the Great Lakes Water Authority. So this is wastewater sludge, exactly what you're thinking of wastewater sludge. Human waste as well as everything else that's in wastewater. It's formatted, it goes through a process that we call hydrothermal liquefaction. From that, you make a material that can be hydrotreated. And from that, we make something that is primarily in the diesel range, and a really high quality diesel. And for us, this is important because as we're thinking about the opportunities to decarbonize the transportation sector, electrification is a wonderful solution for the light duty fleet. When you move into the heavy duty fleet and into aviations and so forth, we have less opportunities. And we really need to have some thoughts of how can we increase the amount of diesel, aviation fuel, and fuels that go into shipping. So next slide, please. So hydrothermal process, it's a technology that uses hot pressurized water to convert solid biopolymers into these liquid components. It's conceptually very simple. You're actually just moving things through a heated pipe. So scalable, robust, it accepts a very diverse range of materials. And for us, what we are really looking for are opportunities to think about materials that are already wet and that we can't afford to dry. And so something in the 20 to 30% solids range is perfect. Of the different opportunities to make fuels, it actually does provide the highest carbon yields of any of these things that we've seen. So 60% of that carbon is going into the fuel. I think Paul mentioned a couple of times that about 30% of the carbon in corn gets into the fuel. Another 30% goes into animal feed. So you're getting of things that are valuable, something similar. And in the case of hydrothermal liquefaction, some of the 40% that is not going into the fuel, most of that is going into things that can also be captured for energy, and we can get about 85% into energy solutions. All right, so the bio crude oil is stable and it can be upgraded. So a little bit here on some of those conditions. And I won't spend too much time on that. So why don't we go to the next slide? So, one of the questions is, can we make a difference though, as we start looking at some of these alternative carbon sources that today are waste that today are providing a liability to people and to the environment. And yeah, and the point is there is enough that we can do something. It won't solve the problem, but it certainly can get us moving in the right direction. So on some studies that have been done at PNNL as well as the National Renewable Energy Laboratory, and taking a look at where are these feedstocks located and that present this liability, how much is available, how much fuel could we make? It would be around 6 billion gallons of fuel could be made. Renewable diesel blend stocks could be produced from these waste sources. And though, that's only about 10% of the diesel that's made today, but it is meaningful. And this is the low-hanging fruit. This is the material that really is easy to get at. So let's take a look at the next slide. As far as the quality of the fuel, one of the things that's quite interesting is the quality of the material is much higher than the quality of the fuel that we can make from wood or from stover or other classical biomass resources. This is just taking a look at the cetane number, and you can see that the cetane number of waste sludge matches that of algae, much higher than that which is required, and significantly higher than what we can get from classical biomass. So the quality of the material that one can make from these waste carbons is very high. Next slide, please. As far as the cost, what is the cost today? It is a little bit high, right? So at 2020, the cost is projected to be in the form a little bit over $4 a gallon. And by 2022, working on how to bring that cost down to where it's closer to around $3. And the biggest issue is increasing the catalyst life. There's some other things that can be done as well. And so this is where the research is being focused in order to further bring this cost down. As I said, the technology is in a pilot stage, and even at some of the higher numbers, the technology with the right incentives is promising, but it needs to be improved. All right, and one more slide, please. So what I wanted to bring up is, we're thinking about biomass beyond those things that are used for food. And the classical lignocellulosic biomass that we have put so much effort into really takes a tremendous amount of capital equipment and separations far beyond what's required for a corn ethanol plant. And because of that, classical biomass is not used today. It's too expensive. Moving to these waste streams does really change the picture, because what we're trying to do is provide an environmental service. And it's really that, how can we look for ways that we can provide this environmental service and then understand these sources of carbon? It was similar to some of the things that Dan talked about when he talked about forestry. And where are there some carbon out of some forest management that could be used? Many of these waste streams are less recalcitrant because they're already partially broken down. And cleanup is important, separations are important. But as these costs come down, then we can start thinking about how do we incorporate and use the technologies from more classical biomass. So I think that's my final slide. Let's go to the next one. Yeah, thank you. I'd just like to acknowledge the people who are doing this type of work at our organization, as well as others. I hope this has been helpful to provide some other thoughts on what we're thinking about in biofuels, the importance of thinking about fuels that can go into things that are difficult to electrify, and the importance of really thinking about other carbon sources than what classically we're using today. So thank you.
Great, thanks so much, John. And so we are still available for time for some Q&A. So I'm going to hand it over to Debbie, who can start getting those questions ready for everyone.